And so here is another possible scenario of peer prediction. So here the requester wants to elicit the crowd's opinions about several fast food restaurants like KFC, Subway, McDonald's, and Panda Express. And in this case, still the requester wants to know who is expert, who really has a lot of information about these fast food restaurants, and also how can she pay the crowds to incentivize them to tell the truth. And still we can see here it's not like the weather forecast setting we have an outcome and can verify the crowd's answers. Here, since their opinions are actually subjective, there is no outcome here. We cannot verify their answer. So still, we want to design this scoring rule F, which takes the crowd's feedback as input, but without any outcome information. And the problem is how to design F in this situation. Okay, so now let's talk about the information elicitation plus information theory. So this is one of the most important thing in my previous works. It's called the mutual information paradigm. So the idea is simple. So first, the requester first asks the crowds to about some questions, and then like for example, there are two participants here, and Alice and Bob. Alice reports her information X, and Bob reports his information Y, and wishfully the requester can magically compute the mutual information between X and Y and use this as a payment. So why we want to use mutual information as a payment is because the information monotonicity of mutual information can directly induce this strategy proof property. So basically, in Alice's view, once she performs some strategies on her information, the mutual information between her information and Bob's reported information will decrease. And in this case, she will choose to tell the truth to report the original information. And the possible strategy can be, for example, she just, in the fast food restaurant's case, she just ignores her true opinions and always say like she likes the restaurants. And this strategy will reduce her payment. And in this case, we can guarantee that the participants will report their original information truthfully. And moreover, in addition to the channel mutual information, any information measure that satisfy information monotonicity can induce this strategy proof property here. Okay. But that is actually a wishful thinking, because the computation of the channel mutual information is always a problem. And to address this challenge, like one thing we can do is we make additional assumption about the structure of X and Y. And another thing we can do is, like in some situation, we need to develop new information monotone information measures that has better property than the channel mutual information. And if you want to know more details about these two approaches, so for the first one, you can refer to the Water from Two Rocks paper, and for the second one, you can refer to the dominantly truthful multi-task peer prediction paper. And the second one actually proposed a new information monotone information measure, such that we can actually estimate this measure with only a small number of samples. Okay, so finally, let's talk about the setting of the semi-supervised learning and its correlation with the previous information theoretic framework. So in the machine learning setting, one basic question is image classification. So basically, we are given a bunch of images, and we want to know whether there is a cat on the image or there is a dog on the image. And if we can have a training data with clean labels, we can of course use supervised learning methods to train the classifier that distinguish dogs and cats. But in some situations, we may only have noisy labels about these training data, especially in the medical image area. Sometimes it's pretty hard to get the pathological truth about the images, but we can easily get some noisy labels about images. And the problem is, how can we train the data with only the noisy labels? And we can see why this is can be a challenging problem here. So let's see this example. So here there is a transition matrix between the clean labels and the noisy labels. So basically, when the ground truth is dog, it still is dog with high probability. But when the ground truth is cat, so maybe this noisy label gonna bias to identify it as dog as well. And in this situation, our noisy label actually biased to one category, which is dog. And if we still use the traditional distance-based measure like cross-entropy, in this case, for the classifier will be trained to bias to dog as well. And actually, for the classifier that always identify all the images as dog, it will has low loss when we train with these biased noisy labels, but it is actually meaningless. So this is one major problem in this noisy label learning area. Okay, so before we talk about how to address this kind of challenge, so let's talk about another setting, which is actually another semi-supervised setting called multi-view learning. So here we are given two views of data. So in this case, like we may given a several pair of data, and for each pair it gives you different views of the animal, and we want to train these two views of data simultaneously to learn the common features. And you can understand as we want to learn the intersection of two sets. And in this case, one natural attempt is going to be if the two hypotheses actually can elicit the common features from the pictures, and then they actually their outputs actually has very low distance. And in this case, maybe we can choose a loss function as the distance between the view A's hypothesis output and view B's hypothesis output. And these two hypotheses, both they want to compress the image to get the features. But in this situation, we still have the same challenge as we mentioned before in the noisy label learning setting. When the two hypotheses, they are meaningless, they always report the same thing. In this case, they actually has the lowest loss in our loss function. And it is actually the same thing as the previous one. We can call it a meaningless hypothesis challenge. The meaningless one can actually has very low loss if we have noisy labels or if we are in this no ground truth multi-view learning setting. And why information theory can help. And the thing is, one conceptual idea is we can change the optimization goal as we want to maximize, this is in the noisy label learning setting, we want to maximize the output of the classifier and the noisy labels. And in this case, if this classifier is meaningless and always report dog, it contains no information, and it has no mutual information with the noisy label, and it will not be selected in our training process. And still the same thing. Here we change the optimization goal as to maximize the mutual information between the view A's hypothesis outputs and view B's hypothesis outputs. And instead in this case, if the meaningless hypothesis always report the same thing, they will have the lowest score here. And this information theoretic idea can conceptually solve the challenge I mentioned before. But in fact, if you want to analyze rigorously and want to get more properties, sometimes you need to develop a new information monotone information measures. And it can give you much better properties than the original Shannon mutual information. And if you want to know more details, so see the LDMI papers and Water from Trucks papers for more details. And the last area is the machine learning plus information elicitation, and still there may be a touch of information theory tools here. And I haven't done any work in this area, and it can be future work. And thanks for listening.